Okay, so we are just talking about these two equations and have just started. So the top one is, of course, total internal energy and is calculated by 3 halves n. What's small n there?
Number of moles.
It's the number of moles, right? Which, of course, is directly correlated to how many molecules are in a particular system. Okay, the R right there, I think, is kind of the most important thing to understand. It will connect to the diatomic conversation that we had and monatomic, blah, blah, blah. If you're not following that right now, just go ahead and assume monatomic right now. There's your equation. We'll burn that bridge when we get to it. But the units on that are joules per mole per Kelvin. Okay? So another way to think of that particular unit is for a set amount of moles, that is joules per Kelvin. Okay? AKA that tells us how much energy there is per 1 degree of Kelvin. How many joules are associated with one specific degree of Kelvin? And then, all right, that's great. Now I can multiply, and that would tell me how much energy, of course, is in 1 mole, right? A single mole, and so I can multiply by the number of moles to get the total energy, and then this 3 halves is over here as well, which, okay, we won't worry about that for right now. Then you have this guy right here, 3 halves kBT. Now, if you remember, kb is another constant, of which its units are also joules per Kelvin. So how is kb different than R? Well, remember that R is actually joules per mole per Kelvin. Kb is joules per Kelvin because Kb is actually a combination of two of the excuse me, two of the constants, which are the R already divided by Avogadro's number. So if I divide, okay, the number of moles by Avogadro's number, do I have those in the right order? Yes, I do. Okay, if I divide that by, then yes, now we're looking at Kb is kind of dealing with not all of the moles, all of the things, but instead a single molecule right here, which is why this would be your average kinetic energy at a particular temperature. Okay, how are we doing ish? Okay, the specifics of that equation we'll get a lot more to next chapter, but the main purpose of this right now is what the heck is U? U is all the kinetic energy. And as I said before, really when it boils down to it, there's only kinetic energy and potential energy. That's it. That's all there really is. So when we say total internal energy, that's the energy. That's it. That's the energy that an object has. That's all of its energy. Okay, it's all the types of energy. So if I want to talk about this guy right here, within reason, there's also some nuclear stuff that we can get into a little bit later on. But ultimately, this object right here has a particular energy because it has a particular temperature and a certain amount of molecules in it. Then we take all those molecules times the average and we get the total, blah, blah, blah. Now, what is Q?
Q is heat.
What is heat?
Transfer energy.
Transfer of energy due to temperature, because technically this is the second transfer of energy. What was the first? Work. And this will actually come up at the very beginning of today. Or for our purposes, just this guy right here. What is work? Well, in general, work is, hey, there's a force going a particular direction, like I'm shoving here to the right. If I shove somebody to the right and they go to the right, basically what we can kind of look at work as is a measurement of, did the object do what I fully expected it to do, right? Like in this room, for example, there's of course a giant force pointing downward. So, you know, all things aside, if you left the room and came back, where would you expect all the objects in this room to be? As far down as they possibly could. If they are not as far down as possible, you would expect something, some other force to potentially be stopping them. For example, the calculators books on your desks right now are not on the floor, but the reason they're not on the floor is because of some force resisting that particular process, yes? If given the choice, if the desk is not in the way, I think this is a pretty fair thing, which one is more likely? Which one is more likely? Obviously being on the floor. So work is naturally done. Work is object moving in place. It is less likely to an object that is more likely. And then its effect of energy comes out in the form of work kinetic energy theorem. So the two big equations to kind of understand are, of course, those when you start talking about energy. But the other way to talk about energy past that is Q. Q is not work. You can do Q without doing any work whatsoever. For example, I'm doing it right now. Am I putting work in the desk?
No.
No. Is any work being done to the desk? Am I changing the desk's internal energy?
Yes.
Yes. So there is a transfer of energy that is not currently being done by work. It is being done by heat. Q is how much energy is going from me into the desk. Yes, Trent?
What's not being done with the molecular level?
We'll get to that next chapter. It's called thermodynamics. There's a whole set of rules.
Go ahead.
Yes, no, you're 100% right, and that will happen next chapter. Let's burn that bridge when we get to it. Okay, so
Every time you try to go ahead.
let's talk about calorimetry. This conversation is going to go quick, but it's probably one of the most important lessons that you learn in this entire chapter. Calorimetry is basically just, well, let's start off with what this box is. It's there's a whole bunch of names for a bunch of things here. I'm trying to remember what this one's specifically called, but I know that there's called it's called a calorimetry bomb, essentially. It's actually how, what's that? What's that? It's called a bomb, but it's not. I promise it's not. All it is really just a container. It's a container that's insulated from the outside environment as best as possible. And the reason why it's insulated from the outside environment is the outside environment is called is I think I mentioned this before, goodness, why am I struggling with this? Heat sink? Nope, not heat sink. Darn it, where's it at? Heat reservoir. Okay, heat reservoir or a cold reservoir. And I say reservoir, there's some external reason why it's going to hold the same temperature. Okay, the external reason in here is there's so much of it that even if we change, if I took for example this room running at say 25 degrees Celsius, okay, and I have a glass of ice water sitting on here, right? What temperature is the ice water? 0 degrees Celsius, very good. So automatically that means there's going to be a flow of heat between the two of them, right? So what would you expect to happen? Well, you would expect obviously the water to inevitably raise, right? Okay, and you'd expect ideally the whole air to decrease, but this is kind of a similar conversation to, let's say I had a cup of coffee and I toss it in a lake. Technically, will the lake cool down? Sorry, heat up.
Yes.
Yes. Is it really going to be noticeable?
No.
Let's call it a cold reservoir in that case, because basically it's going to stay the same temperature. It's kind of like when you're dealing with the air in this room. Are we heating up the air? Yes, but due to AC and everything is the air in this room really changing temperature? No, it's a reservoir. So what we're looking at right here is trying to isolate those reservoirs and look at something that happens in here. So this is the bomb cell right in here. This is the sample material. A sample could just be some piece of metal. Okay, and basically put, this looks way more complicated than what I'm trying to go for right now. Essentially, imagine I had a really hot piece of metal, okay, and I dropped it in water. Okay, the water is room temperature. So let's say the hot piece of metal is 70 degrees Celsius or something like that. I drop it in water. What should the water do? Heat up, okay, and what should the metal do? Cool down. And essentially what's being said there, oops, going the wrong way. What we would expect to have happen is that the Q cold, the energy that is, would the cold thing gain or lose? Would gain, correct? As a matter of fact, what is the equation for Q?
MC delta Q.
Correct? So be careful with this guy, so I can put it over here on the board, MC delta T. Be careful with this little guy right here, because that's going to change signs on you. Why is this positive? Well, because it's gaining energy. But more importantly, mathematically, why is it positive? Because that is positive, right? And change in temperature, as always, and this becomes very important later on, is what? How do you get the change in anything? Final minus initial. So the other way to write this is, of course, MC times T minus T0. Or if for some reason you prefer final and initial, that's completely fine. I don't, but that's entirely up to you. Sorry, I should have put that on the slides because we're recording, so I'll do it again real fast if I can actually spot where the heck I have lost it once again. So once again, the equation is Q equals MC delta T. The cold thing is positive, of course, because it's gaining energy, but mathematically it's positive because the change in temperature is positive. and vice versa for the hot thing. Why is it negative?
Because it's
Losing energy, but mathematically it's negative, of course, because delta T is going to be negative, because in actuality Q is mc times T minus T0, or like I said a second ago, if you prefer final minus initial, aka if final is bigger than initial, cold thing gets hot, right? If final is lower than initial, hot thing gets cold, and it would go the way we would expect it to go. So the calorimetry bond is actually a direct connection over to energy. I told you that energy is defined by work, and it absolutely is. So if you actually look at this setup, this is actually a lot more fancy than we're going to use it for when we have the lab. This setup is basically just saying this: hey, if I put in mechanical energy of so many joules, I should actually be able to measure how much temperature that raises. The first setup that actually proved the calorie was this. There was a mass over here on the side that had a pulley. The pulley was connected to a stirrer. So what they would then do is they would take a certain amount of mass, let's say 1 kilogram or 9.8 newtons, and let it fall. Why would they let it fall? Well, because that, of course, would do work on the mass, which in turn would do the exact same amount of work to the water. And so they figured out that when they let that 1 kilogram mass, that'd be 4.9 newtons, fall roughly a little bit less than half a meter. I say a little bit less than half a meter because that would get us, I don't know, 4.200 joules of energy. They would find that 1 gram of water would increase by 1 degree, thus giving them 1 calorie is equal to 4.2, or the 4.11, or whatever, I can't really say. 4.2 is what I would just use, joules. So how am I going to do calorimetry? Well, let's imagine that we've got 3 things, 3 objects in this case. There is not just 2, there is 3, because the aluminum beaker by itself, we'll say, starts off at room temperature. And we have some hot water, okay, hotter than room temperature, so it's going to be 40 degrees. And the aluminum is certainly hot, but it is not as hot as the water. And they put that all in right there, using that equation like we just said. And here's the equation that you're going to use. There's sigma again for you. Okay, your sigma is this, your standard equation. You know how the energy equation always started in one of 2 spots. It was either conservation of energy or sorry, help me out. Work-net kinetic energy theorem. This actually is conservation of energy. Okay, conservation of energy, but it's done that way for temperature. What is conservation of energy now? Sum of Q's are going to be equal to 0. Why?
One thing heats up, the other thing cools down.
Right. Okay, and or probably another way to say that is energy has to be conserved. If one thing loses 10 joules, the other is going to gain 10 joules. Now, that's easy to deal with when you have 2 objects. It's less easy to deal with when you have 3. So, for example, in this case, what they're going to show you in a second is that there is the Q of the water plus the Q of the aluminum plus the Q of the, what am I missing? The sample, or the, I thought the aluminum was the beaker. What was it? No, the aluminum, you're right, the beaker. My apologies. Thank you. Now, you will notice something really nice about what I just did, and that is I did not worry about positives or negatives whatsoever. Why not?
Because you'll be able to.
The delta T's that are buried inside of each of these will take care of positives and negatives, and one will go up and the other will go down, but in total it has to equal 0. Another way to look at that technically is this, going back to an equation that you guys have seen, just to kind of make a comparison real quick so you can see it. We did this a ton, so I'm not expecting you to do it right now, okay? The good old days, yeah. But if I took all of these and subtracted them on the other side, what you would get is final minus initial, minus initial, final minus initial, right? Or in other words, the change in gravitational energy plus the change in elastic energy plus the, screw that one up, plus the change in kinetic energy has to equal 0, right? So basically that other equation is this right here. The nice thing is you can just write this at the very beginning of your page before you figured anything out, and you just have to put Q's of all of the objects in a particular situation. Now, if you had to guess, There should be some easy ones here. Are you going to guess that Q of water is going to be positive or negative? There is a correct answer here. It's going to be negative. How do you know? Based on the numbers. It's the highest temp, and thus it will definitely come down. Okay? And so, of course, which one up here is definitely going to be positive? The beaker will definitely be positive. Now, aluminum, we technically don't know. It could be either. We could make a guess. Since it's only 3 degrees away from water, I might say it's a pretty good chance of going down, but don't forget that water has such a ridiculously high specific heat that it might take such a large amount of energy for this to come down that actually it requires some of the aluminums in order to get to that particular spot as well. So it's easy. Like if the final temperature, which you can calculate, I'll get to that in just a second. Actually, I'll show you briefly without finishing the problem. If the final temperature is 38, okay, well then obviously then this was positive, right? Now, how can I do that? The next step on all of these is always going to be the mass of the water times the specific heat of the water times the change in temperature. Now, if you are looking for that final temperature, though, how you're going to want to write that is times T minus T0 of water, or I guess tau. Plus mass of aluminum times specific heat aluminum times T. Now notice that I have got that variable exactly the same. How come?
Because they're all the same.
They will all end at the exact same final temperature. So, as complicated as this algebra is going to be, I'm just going to use B for this. This would matter what it's probably aluminum, so it probably actually is the exact same specific heat as this guy over here, but I'll just say beaker for right now. As complicated as this looks, how many variables would probably be in this? Assume I gave you all the masses.
No.
Well, all the masses are just given based on what I just said. All the specific heats are all constants, so all you need to know is the material, which I'm pretty sure it tells you. All the initial times, sorry, all the initial temperatures, not times. All the initial temperatures were given to you, so what is the only variable? The final T. Yeah. Now, I apologize about some of this math. It does get a little bit icky and that type of deal, so yeah, you do have to distribute this out to both, and it actually ends up to 6 separate terms, blah, blah, blah. We'll burn that bridge when we get to it. All right. Questions, concerns about calorimetry? Basically, this whole thing was trying to make sure that you understand the general structure of how to do a calorimetry problem, how you're going to be expected to do those calorimetry problems. Try them on the homework. We will probably spend a little bit of time in here, especially when doing the lab over the course of probably a couple days of messing around with Q as well. Please practice Q as soon as you can. Yeah, it's not too bad. But again, how do I start? Just like you start with like a lot of the equations and build out, it's always going to be exactly the same here. Sum of Q's equals 0. I don't know why they have QK. I'm not sure what the K is for,
In the
but
book
you
it
got it.
says they have the K there for the amount of things involved.
Oh, interesting. Okay, so like 3? Interesting.
Yeah,
So
the K would be 3.
I wouldn't worry about it myself. I'm going to write sum of Q equals 0 when I do mine. So yeah, and then you just write, like I said, you don't need to worry about positive or negative. You do not assign positive or negative. That's going to come from your temperatures. So you can just straight up just write the Q's of all the objects, start filling out their equations, and then algebra from there. All right. That's section 3. Let's talk about latent heat and phase change. So there are 2 types of heat. There's really not, but there's 2 types of equation for heat, I should say. Q is Q is Q, okay? But what you're looking at right here is that imagine that I do have a sample of ice sitting in a cup in my hand, okay? Basically, assuming that other certain variables are controlled, that ice has to entirely become water before its temperature can change. Does that make sense? I'm going to kind of walk through this. I'm sure it's pretty easy, but I'm just going to basically explain that sentence. If you get that sentence, you got to tune out me for like 30 seconds. Okay, the basic gist is this, that ice there's bonds that are essentially holding that kind of in place. The bonds are the positives within the nucleus, the negatives in the other, and it's holding that guy in place. And as we discussed last chapter, ice is weird because it snaps into a particular crystalline structure, right? That crystalline structure then takes energy to break those bonds, but not change the temperature. Does that make sense? Temperature, kind of you can think of the speed, how fast they're going. They're wiggling at a particular speed, and thus they have a temperature right next to each other, right? Whereas to separate them, because there's a bond between the positives and the negatives over here, that's going to take energy or work to separate, even if these are still wiggling at the exact same speed as before, right? Okay, and why do they have to stay at the same temperature? Well, let's say in that ice, you take a chunk off and you make it water. Why can't that water then get above 0 degrees? Still touching ice, and that ice is going to be at 0 degrees. So where's all the extra energy going to go? If it can't go into the water increasing, it's going to go back into the ice and breaking it back down into water, and vice versa. Now, L is essentially what's known as latent heat. Okay, this is a simple, another constant when you're dealing with this. That constant is simply, look at the units right here, joules per kilogram. Simply put, that is how much energy to take 1 kilogram of that object and change its phase. Now, unlike the calorimetry equation I said just a second ago, with Q equaling mc delta T, there's a change in temperature. Obviously, you don't see a change in temperature up here because of what we just said. Okay, so that doesn't matter. But you will notice there is a plus or minus now, meaning in the last equation I told you don't worry about it, it'll take care of itself. Here, obviously, you do have to worry about it. What will decide whether or not you are getting a positive or a negative?
Just going up or down.
Try that a little bit differently.
Like base changing to like a liquid or solid.
Okay, so which one's which?
Solid down, liquid up.
That doesn't.
Positive.
You need to give me the whole transition. That's not quite what you're.
Whether it's changing.
From liquid to solid would be. Q would go. Liquid to solid would be negative. Why? Losing energy. I have to pull energy out of it in order for those bonds to basically form. Or another way to say that is if I want to, which has more energy? A solid amount of mass or the same amount of mass of water? The water. The water in this particular case, and thus it takes energy to go from, or here's an easy way to put that. Do you heat up to get this way? Do you add energy? Or do you cool down, take away energy to pull this particular process off, right? So in the case of going from solid to liquid, it would be positive, and liquid to solid is, of course, negative. Now, just in case, I'm sure you remember this, but melting point, when we're talking about melting, you're usually used to one direction, but technically it's sort of the melting point happens for both directions. Right? Melting point is both where melting will happen, aka going from solid to liquid, but it's also where freezing happens from liquid back to solid. So your melting point tells you where it's going to happen. Your latent heat, latent heat of fusion. Fusion goes hand in hand with either direction. These are your constants. That is your constant L. Make sense? Okay. Then, of course, you have vaporization, which goes hand in hand with boiling. And boiling, once again, is not just liquid to gas, but also, well, there's a different name for it. Gas back to liquid is condensation. Very good. And, of course, if we really want to get into, which we're not going to do right now, for the sake of chemistry, the whole pressure wheel and that type of conversation of making skips so that we can deal with sublimation and disposition, blah, blah, blah. We're not going to worry about that here. We're just going to worry about these guys for right now. So, for water, and you'll notice this is already up there, you'll notice that the latent heat of fusion is 3.33 times 10 to the 5th, and the latent heat of vaporization is 2.26 times 10 to the 6th. What does that mean? It means that 1 kilogram of water, which requires more energy. Does it require more energy to go from solid to liquid, or more to go from liquid to gas? which is why you definitely don't want a steam burn, because there's so much freaking energy still in steam. You have to be extraordinarily careful, not just of being burnt by water, but being burnt by steam, because there's a ridiculous amount of energy in that. Okay, so let's look at, for example, what if I want to take an object and I want to take it from ice down here at negative 30 degrees Celsius, and I want to go all the way up to, let's say, 120 degrees. Okay. Now you love to, if you're not carefully thinking about it, you go, oh, well, it's changing temperature, so that means I'm just going to go QMC delta T. But there's two things that need to be addressed. The first of which we would use Q equals MC delta T from this guy right here, negative 30 to 0, because we're changing temperature. Yes, to get to the melting point. So if I wanted that Q, boom, there it is. I think they're using just a gram. So this is why it's 1 times 10 to the negative third. Here's my equation. Now, what I would do if I were you is I would call this Q of ice. Okay? I would call this Q of ice. Using your subscripts, well, yes, obviously it's all water, but we're going to need to make some separation, and you'll see why. Actually, I'll tell you why, one of the reasons right now. What is the specific heat of water? Does anybody remember? You're doing calories. I actually want joules in this case. You should know this one. Oh, you're close, but that's the one calorie. This is a kilogram right here. Usually when you do this, so 4,186. Okay, 4,186. Is that the specific heat they're using? Why not? Because the specific heat of ice and the specific heat of water are not the same. Reasons that I don't want to get into right now, because I want to hit a few other things. But again, I go back to what I talked about at the beginning of like that experimental physics versus like theoretical physics. You're asking the theoretical physics question. I think most of us, should take like, who cares? They've measured it. It is what it is. That is what it is. Yes.
Do different materials have like different specific heats depending on the phase on it?
Yes, they do. But for the most part, because of the generalized temperatures that you and I deal with, you don't usually have to deal with liquid iron. And if you did have to deal with liquid iron, I'm going to go ahead and guess you should go ahead and try to figure out what that specific heat is, or there's gigantic books full of this stuff as well. Yeah, so yes, they're 100%, you're right. You will note that on the table of specific heats, I'm going to go all the way back here real quick. Let's go fast. Come on. Well, that was cool. Oh, there it is. Okay. Okay. These are specific heats of some materials at atmospheric pressure. Okay. So at atmospheric pressure would be 1 atm. So for the most part, what you can kind of think of, if this thing at room temperature is a particular liquid, gas, solid, that's what you have specific heats for. For example, ethyl alcohol in this case is more than likely a liquid, which is why it's pretty darn close to water in that particular case. It's higher, closer to specific water than anything. So yeah, that's obviously going to be a liquid. Copper, cadmium, beryllium, and aluminum, if you didn't know, are definitely solids. So you can assume solid in that particular case. I believe, if I'm not mistaken, up here, the only phase change we have is in fact with water, with having steam as well as ice on there as well. Unless I guess human tissue is a little bit gooey, but yes.
Yeah, that's what I was about to say. You said that the reasoning behind ethyl alcohol being a liquid is because it's close to water, but human tissue is closer to water.
100% it is. I was just saying it was a liquid, thus bringing it close to water. Now, here's an interesting thing about this particular table. The way these were calculated was with the calorimetry bomb. Okay. Calorimetry bombs, in a nutshell, this is way too much of a simplification, is also how we get the calories out of food. Basically, you put in a piece of food in a particular calorimetry bomb, and you measure basically how much it can burn. And how do you figure out how much it can burn? Well, you basically pretty much light it on fire. You give it some kick, you give it some go, put some water on the outside, and measure probably what about the water. How much the change in temperature is. If you then know the mass of that water, the change in temperature and specific heat, you can figure out how much Q the water just got, and thus you can get how many calories are in the water, or in the food. Now, what's interesting about the air quotes I'm putting up there right now is your body does not tear food apart the exact same way. It's not lighting stuff on fire. It is tearing it apart in a different way. So in truth, calories are just kind of a relative scale, meaning that that's not exactly how much energy is inside of you. But you can look at something with 10 calories and 20 with calories and go, well, that one obviously has more, probably double than the other, even though you were not taking that exact amount of energy. So my analogy and my example that I've done like twice at least, we're climbing the stairs and you've got soda and this is exactly how much you should climb. It's 100% inaccurate because actually we're a lot more inefficient with turning out that energy than setting it on fire would be. So yeah, we'll take that with a grain of salt 10 first.
So since it says at atmospheric pressure on the table, does that mean that there's different specific heats at different pressures, or is it just?
Yes.
So wouldn't that mean at a different pressure it has less energy at the same temperature?
Yeah. So there's a whole like set of conversation here, and what I always say with this is like, if when you guys eventually, some of you go out and like actually do lab work, what you'll find is that none of those labs ever pull a number off of a table. What do? They go to the lab and they actually measure what it actually is for them specifically in that specific set of environment and controlling all of those variables as best as possible. Trying to keep atmospheric exactly the same. Does it need to be a particular number? No, but we need to keep it the same so it's not affecting those particular numbers of whatever it is I need to be calculating. Before I actually do the calculations, I want to know these constant, and they're going to figure out the constants for themselves specifically. Does that make sense? Yeah. Fair enough. Yes?
Is there a way to measure like the joules per kilogram at a temperature without a calorie bomb or whatever it is?
Yeah, but I mean, this is definitely the easiest thing.
Because how would they like find human tissues? Like,
so I was actually starting this conversation, and I kind of got sidetracked on that because I wanted to talk about human tissue. That means they put human tissue in a calorimetry bomb and just set it on fire a few times in order to get that particular number. So, to a certain degree, Trenton's question of like, why are they different? But they are. And to a certain degree, that's experimental physics. Okay? It feels weird, but experimental physics is probably one of the most raw sciences you get because we go like, what is science actuality? It's not actually theoretical science. It's not the heart of science. The heart of science is going, what happens when I do this? I don't know if I trust that. Let's do it again. All right, do it 500 more times, measure the particular results, write it down in a result, write up a report saying that when you do this, this happens. Okay? And then somebody goes, why? Somebody else goes, who cares? It happens. Okay? That was just the argument between experimental physicists and theoretical physicists. Experimental, it happened. Theoretical, why? You're asking dumb questions. It happened. Also, a little bit of the conversation between physicists and engineers as well. We don't care why, it just does. All right, now let's continue. So, point is, going back to the beginning, I'm using M, which is a gram. I'm using C, which of course is this because it's ice. And I'm using this, which is 30. Why is it 30? Because I started at negative 30, and melting point is 0. Good news for you is most phase change problems are almost always going to deal with ice, so you do not usually have to memorize the melting points of like all of the things, even though you have them on that other table. But now, let's go to, all right, so what do we have now? We have a gram of ice at 0 degrees. It is ice, right? Now, what's interesting about this graph, which I love, is it shows you essentially this. It shows you the energy, like, total kind of how much is going into this. You see, there actually wasn't that much energy whatsoever. Now, let's look at B. Okay, how do I get B? Well, this is the latent heat conversation from before. Okay, I take the mass, 1 gram, and I take 3.33 times 10 to the 5th. Did I say steam had more? It's definitely this one. I still totally screwed up because I just used the wrong number. But yeah, we use this constant, which we got from the previous table because it's latent heat, and that's how much energy it takes to do what? That's how much energy
turn into water.
Take to go from 1 gram of ice at 0 degrees Celsius to 1 gram of water at 0 degrees Celsius. Right? Obviously, what kind of happens here if I increase the kilograms? Well, obviously, the energies go up. right? Because it's going to take more energy to pull off this particular process. Then I look at water. The rest of this is going to go pretty fast because it is basically a repeat. Just exactly the same, because now we're getting change in temperature, so that's that earlier equation. The mass is still 1 gram. Now we are at that 4.186, or they're using 4.19 times 10 to the third for some reason. And of course, right over here we have 100. Why is it 100? Because we're going from 0 all the way to 100. Now, a lot of your problems are not going to make you do all 5 steps. A lot of your problems are going to say, hey, a piece of ice at negative 30 degrees Celsius needs to go to 76 degrees Celsius. How much energy will that take? Not telling you any of these other steps that are obviously going to be in the way. So what people wouldn't be careful with, what people screw up with if they're not that careful, is they go, oh, I started at negative 30, I go to 76, I'm just going to use this equation, and not check for the phase change potentially in between. Had, of course, you gone to 76, well, then this would just be 76 and would be done. But it's not. It's 4,190, and then we would get D. And what is D? That is the heat of vaporization. Okay? Oh, I didn't talk about subscripts. Here's what I would have. I would have, because I think it's helpful to know, I would call this Q ice, like I said. I would call this QF for fusion. Okay, which you want to get used to, using F specifically for talking about that transfer. So I don't because what letter do I use? Do I use ice or water? Well, technically it's changing between the two, so that's why we use F for that. This, of course, I would probably use either QW, or if you want to use QH2O, being fancy, that's great. And then right up here, when I do this guy, I'm going to call that QV for vaporization in this particular case. And that would just be, again, the mass times the latent heat of vaporization to get how much energy it takes to do what, real quick, and then I'll answer you. Let me finish this slide because I'm almost done, I'm rolling. But what is this to do? This is the energy to do what?
1 gram of water.
Thank you very much. And then finally, of course, because it said it wanted to end at 120, boom, we do this last thing. And of course, this C over here is for steam. You will notice that steam and ice are very close together, but not quite the same as one another to get that. And then, of course, finishing off this process, if we add them all together, it looks like that. What I would probably do if I were you, okay, is just like I kind of earlier talked about, setting up these problems. These are calorimetry problems, assuming they're going to end at the same temperature. This is not ending at the same temperature. This is looking at one particular object. Always. I would say this. I would say the sum of Q's in this case is not going to be 0 because it's going to take some energy coming in, is equal to Q of ice plus Q of V plus Q of water plus Q of fusion plus Q of steam. And then I would honestly not do them individually like they just did. I'd plug all of those equations up there at the same time, plug your numbers in, and get a final answer. Sorry, Jaden, what was your question, comment, concern?
What does fusion mean? Like, is it solid to liquid, or is it?
It's vaporization is between liquid and solid. Fusion, sorry, backwards of that. Fusion is between solid and liquid, and vaporization is between liquid and gas.
Does it matter the order?
No, it's whichever direction. Basically, that's the process. This is the constant either way. The only thing that'll change about that equation, actually, you humor me here, okay? If I go back over here, what would change about this equation if I was going instead from ice down to, from steam all the way down to ice?
Negatives?
Careful, because some should get negatives, not all of them. This one would get a negative, and this one would get a negative. Why do the other ones not? In the delta T should be taking care of that already. Or another way to say that is, if you know, all of those delta T's we were dealing with would have been negative instead, right? So I don't usually address the negative in that particular case. All right. I'm not going to worry about that. So this is just telling you what I said just a second ago. This is how you would set up the problem. There's your tables right there. Okay. For conservation of energy, boom. Yeah. All right. Last example today. All right. Yes. What's up?
Why do you add all of the Q's?
Me personally, or what?
No. Okay. So
in that particular problem, the question that was being asked is how much energy has to be added to pull this off.
Well, okay. So when you're like changing temperature, you're increasing the energy.
Okay.
When you're changing state, you're also increasing the energy.
Agreed.
You're getting both of this extra energy from the outside source, right? Okay. Why isn't it using some of the energy it got from changing temperature to do the changing state?
Well, that's what we were talking about earlier. It's the answer. The statement that I said earlier is, why does the entire sample have to change state before it changes temperature? And the answer is, if I have 0 degree water right here and 0 degree ice, will some of that water potentially jump up to 1? Individually, if you looked at them, maybe like a few molecules might. But what is that extra speed going to be doing as it runs into the bonds of ice? It's going to break that bonds of ice, and it's going to slow that water back down and slow that water back down to 0.
Is that just a water thing?
No, that's a state thing, period. That's a state. I mean, and again, you can kind of logically play this out, like, okay, why can't, if I looked at 10 molecules, right, and these molecules, these 5 over here are ice, okay, and these 5 have already become water, why can't they scoot away and just go faster? Well, because again, they're all kind of combined in this area. If they were more spread out, like if you put a cube of ice like on this table and they were not in direct thermal contact, 100% it could be different, right? 100%. If I had a thing of ice and the water from the base started spreading out, could I actually measure that the temperature of this water over here is above 0 and this over here is closer to 0? Yes. But we are looking at systems that are kind of like held in equilibrium, aka imagine it's in a cup, they're in thermal contact with each other the entire time. That's why. Does that make sense? Yeah. Okay. One more question on this, and let's do this. Okay, I'm going to ask you a question that I think you should be able to answer pretty quick. Okay, if I took this ice and added 400 joules, what would happen? So this is, by the way, these calculations that we have up here are if I took a gram of ice and I needed to get all the way up to 120 degrees. What would be the, excuse me, how much energy would it take? So this is kind of giving you all these breaks. I'm saying if you have 1 gram of water, and we kind of reverse this process, you put in 400 joules of energy, what would happen?
Hot water.
Not hot water. I think you'd have cold water. Okay, how do we do that? Well, it would take 62.7 to get up to 0. So would it still get up to 0?
Oh.
Yes. Okay, and it takes 333, of course, to get to water. So all of it is now water because I've used 400. And I think, if I'm not mistaken, I have like maybe 4 or 5 joules left. So am I going to be above 0? Technically. But I'm going to guess on a calculator we would probably round and say, yeah, it's mostly 0 in that case. All right. Give me a 0 to 5 how we're feeling right now. Just to 5. Cool beans, looking pretty good. Let's go. Last section. Thermal conductivity. So I've kind of been avoiding this. What we've been dealing with is systems in which you've got a set amount of heat over here, a set amount of internal energy over here, a set amount of internal energy over here. We've got 2 objects next to each other, and, excuse me. So you've got object A, object B. We fully expect them to get to the same temperature, meaning I expect there to be a loss of Q, right, for a loss of Q and a gain of Q that is the same, aka all of the Q's have to equal 0. Now, this would be something very similar to energy and the conservation of energy that I had on the other page, which is this. Do you remember what the assumption was? Where'd you go? I had you up here a minute ago. Did you go this way? Where'd you go? Come on. Yeah, I lost it. I lost it. Come on. What was the assumption, basically, about the conservation of energy? I'll go find it again. I'll just write it.
No energy.
There it is. Close.
So we're non-conservative for it.
No non-conservative, or you could say there's no energy, or let's say it a little bit differently, because you're absolutely right. There's no external energy being added or taken away. And we made that more accurate by doing this later on. We said mechanical energy initial plus the work of non-conservative is equal to the mechanical energy final. If you change the words non-conservative to just outside source, basically if you don't add energy in or take energy away, we should expect the energy to stay the same. Yes? Okay? That's sort of, and watch here, if I move this around, this just says, hey, however much energy I add or take away is how much this should change. So if I don't, then obviously the change should be 0. This equation is identical essentially to this equation for calorimetry. However, we've already discussed a few systems with a heat source, a heat reservoir, or a cold reservoir that I am continuously putting heat out right now. Technically, if we had a ticker tape over top of my head that is actually measuring this, of how much heat Spainhour is putting out in this class period, what's that number doing? What's that? Constantly going up. And if it's and by the way, that should obviously be the case for all of you, and I would hope that it would, because that would make me a surviving, successful human. That's how we were made. We are a heat sink to lose this because we're doing processes all the time. By the way, if you were not a heat sink, what would sadly happen to you? In other words, if you didn't shed that extra heat, what would happen? You better not use any energy. Because if you did use energy, where's the excess go? It goes to the temperature, and then, as we discussed previously, increasing the temperature is going to screw up that whole process. So I'm automatically needing to use energy, so I better be shedding energy in that time, and hopefully overall, for the sake of my temperature, the amount of energy that I am shedding and the amount of energy that I'm using is the same, so that my net temperature stays the same, homeostasis. Okay. I had this conversation very similarly when we talked about energy before. It was this: if I have a ball roll down a hill, it makes sense to talk about it in terms of amounts of energy, because the ball is going to roll down the hill and stop. It's going to use a set amount of energy. A set amount of energy is going to come out. Cool. But it doesn't make sense in talking about somebody like Buff Spainhour lifting particular materials. Why? Does Spainhour have a set amount of energy? Well, okay, this is a little bit of weird. Do I have a set amount of energy right now? Right now?
Yes.
Yes. What is that set amount of energy based on? How much food I have eaten and how much energy I have stored in my fat. That being said, I regularly am increasing that amount of energy, of course, by eating. Or take your car. Obviously, what do you do to give energy to your car? You put gas in it, but as long as there's gas in it, it continuously put out energy over time. There is not a set amount like that ball on the hill. So rather than just talk about a certain amount of energy, what makes a lot more sense is to talk about how quickly you can put out that energy. And we say quick, of course, it's not a velocity. Quick always means compare the thing to time. Right? If I'm eating a bowl of cereal and you say I eat the bowl quickly, you're not saying that I'm sprinting while doing it. You're really saying what? We'll say that differently. So you're just kind of changing it. What does it mean if I do something fast?
You're doing it in a low amount of time.
Time is low. You're actually looking at time and going, it took you a smaller amount of time to do the thing than I expected you to do the thing, right? So anytime, basically, if you're fast, what you're really saying is it's a rate, and if you say a rate, you're making a ratio, and what is always on the bottom of that ratio? Time. So we're looking at energy relative to time, otherwise known as power. So as I talk about Spainhour shedding heat, probably what makes a lot more sense is not how much Q Spainhour is putting out, but how much power Spainhour is putting out. Or you, I'm going to get off of this because of your propensity for the Buff Spainhour conversation. All right. So for example, last night, I actually made pasta at our house, and I put a bowl of water in there, and I kind of got a little bit irritated because the pasta called for 4 quarts of water, which if you ever put 4 quarts, that's a lot of water. Okay, and I didn't think the pasta needed that, and also my kids losing their ever-loving mind, so I chose to do 2 quarts of water. I think it's kind of simple, but we can talk about it, right? It's not a problem. Okay, why is 2 quarts of water certainly going to help me in the form of time?
It's not as much water, so it'll do that fast.
It's not as much water, so it will take less heat to change its temperature by a certain amount. And so now we are going to change this equation for this particular purpose right here away from that one to that one. That's a different conversation, but it's the same conversation. Yes? Mm-hmm. What are the units of work? Joules. What are the units of time? What are the units of heat? joules. What are the units of time? Seconds. And so that means both of these powers have the exact same units, which are otherwise known as what? What? All right.
Oh my God.
Every time! Even you saw it before! How did you not see it coming? All right, I love it too much. All right, my apologies. No. This amount of water takes a certain amount of Q in order to change its particular temperature. To give that Q, I did not get a bunch of hot things and keep throwing them into the water and make sure all of them were 100 degrees plus in order to make that happen. Of course, what I did is I turned it on the burner, I switched the burner on, and it used electricity to put out a particular amount of heat, and it put out that particular amount of heat over time. So let's discuss what we can do to understand this equation a little bit better. Power is Q over an amount of time, and it's proportional to area, change in temperature, and disproportional to delta X. Let's just talk about that briefly. We're not going to get a ton into this, but my theoretical physicists would get irritated at me in here if I didn't at least have a small conversation about it. Why does area make sense? That if I increase the area, I should get more flow of it? Well, let's start with this. When we say power, ultimately this is hot, T hot, real quick, the heat reservoir. Let's assume that this thing is the same temperature over here the entire time, because for the most part it is, all right? Why? What's happening in this material as I put heat into this side of the material? These things are wiggling faster. And of course knocking into these, which are wiggling faster, and knocking into these, and eventually that wiggle moves across this very slowly, but eventually gets to this other side. So why on earth would it make sense to have more area deliver more energy? More collisions. If you double the area, I don't know how many, but I can guarantee that you have doubled the amount of collisions, and thus you have doubled how much energy you put out in the exact same amount of time. Make sense? Thus, the proportional thing, we're not using the equal sign yet. Let's talk about change in temperature. Change in temperature in this case is not quite the same, almost the same as Q's. Change in temperature in this case is not final minus initial, it is hot minus cold. The most important thing to get out of this is absolutely a magnitude, and we are not at all worried about positive or negative here, okay? The hot is always first, the cold is always second, okay? So the change in temperature is simply going to be hot minus cold. It's always going to be a positive number. Why would it make sense that a greater change in temperature would cause more power? Well, imagine this. I've got 50 degrees over here and 0 degrees over here. And then I have 100 degrees over here and 0. 100 means these things are, of course, going to be moving way, 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 way faster. Yes? Now, lastly, to talk about delta X. What you want to think about happening, if I talk about this is hot at 100 and this over here is cold at 0, what is happening in the intermediate here is it is linearly changing the temperature. If you could somehow look layer by layer by layer by layer by layer, okay, what is the middle temperature going to be? 50 degrees. 1/4 over here, 75. 1/4 over there should be 25. Yes, so it's this. So why does it make sense that the increasing delta X, or the thickness of the material, should then instead decrease the power?
It'll take more time to transfer the heat.
There it is. It's the same amount of energy transfer, but if I double the delta X, it's going to take twice the amount of time to get across. Now again, these are moving very quickly. It's not much time, but twice the distance means twice that amount of time. Does that make sense? Cool. Now, the great thing that we always do in physics 2, whenever something gets way too complicated, is we figure out what's proportional, and then after that, what do we always do? Make a constant. Correct. So, oh, I'm sorry. This is just talking about what I just said a second ago. Delta T, notice, is a little different on this. Again, it's not final minus initial. It's always hot minus cold. And again, it's always going to be positive. In this particular case, oftentimes delta X is going to be seen as L, okay? And therefore, the ratio of delta T over delta X is just TH, blah, blah, blah. This is what we just talked about a second ago. Notice again, this is important for definitely next chapter. Pictorially wise, if you ever see these like red spots and these blue spots, that is telling you that in that picture, that is a heat reservoir or a cold reservoir. And again, that means Something externally is holding that temperature, whatever we say it is. So if they say the heat reservoir is 100, you can imagine next to it is a burner that is staying at 100 degrees because extra energy is coming in to keep it at 100. Right? If that burner at 100 is next to like this piece of metal, technically it should get a little colder as it loses that energy. The only reason it's not getting colder is something's adding that energy back in to keep it at 100. Same thing with 0 degrees, although 0 degrees is a little weirder because you have to take energy out. We're not going to worry about that yet. You can imagine basically if this is 0 degrees, like an ice bath. It's stable. Or probably your best example is like a window, right? In here is roughly 25 degrees. When it gets cold this winter, let's say it gets freezing outside, that would mean the temperature on the outside of the window is 0 degrees. Now, is there technically power and energy happening through that window over here that is causing the outside to get a little bit warmer and the inside to get a little bit hotter? Yes. However, as we add that energy to the outside, similar to the coffee example earlier, would you expect the outside's temperature to ever be noticeably different due to the large amount? Thus, we call it a cold reservoir. It's staying at 0, even though it technically wouldn't. And why on the inside would you probably not expect that temperature to change? AC. Yeah. AC is attempting as best as possible that you are losing. Like right now, we are all heating up this room, but we are regularly attempting to pump relatively cold air into this room and then back out of this room so that it pulls that heat out of the room and the temperature stays the exact same temperature. If you're really interested in everything I just said, get into HVAC. You're going to make way more money than I ever will. All right, and you'll actually have a pretty fun life. All right, so there it is. There is the actual equation for power. Okay, power equals KATH minus TC. You'll notice the A is area, like we just got done talking about. TH minus TC is the change in temperature. L is just the thickness of the material. All of those we've already addressed. So guess what K is? That's the constant. It's the thermal conductivity of whatever material it is. We'll see a table of those here in just a second. But do love them some K, yes. I apologize. I wish that I could choose the letters for you. I think I could do a little bit better of a job, but yeah, there's some weird. And then what's worse is you'll go take another physics class and they'll change the letter. Ooh, that doesn't feel right. That'll mess with you harder than anything. It would be like I think you're fine with it now, but essentially it would be like if I gave you this kinematic equation. Let's go. Boom! You know that kinematic equation. 100% accurate. Looks like what's up?
How do freezers constantly take away energy?
See next chapter, and you'll be sad for asking that question then. But let's talk about that next chapter. Yes.
Physics 1, like not AP Physics 1, doesn't use ME for mechanical energy, and it made me mad.
I'm sorry.
Actually, I was just because you commented on like the change of stuff.
Sure. Yeah. But here's the other one. Oftentimes they use PE for potential energy instead of U, like we use. Do you know why I use U and not PE?
Science uses U.
There's actually a dumber reason. But technically, I do have that to fall back on. The AP test uses U, but even if it didn't, I would. Why?
Power.
It's a dumb answer. It's a dumb reason.
All the other letters are mostly used.
I have to write potential energy a lot. It's one letter short. That's it. That's it.
And U is
all right.
a really easy letter too.
And I don't want to use P because power. Yeah. And momentum. Well, technically it's a capital P. Yeah. Capitals and lowercase. Make sure you're getting these right. So here's your equation for thermal conductivity. You are mostly going to be using the top part, those metals, and notice that those are at 25 degrees Celsius because, roughly speaking, that's the average accepted room temp, although I think 25 degrees Celsius is actually, I'm trying to remember, 25, 77 degrees. It's a bit, I would say a bit warm for room temp, but whatever. All right. So, there you go. Now, there is one other thing. Okay, now, two rods of the same length and diameter are made from different materials. So I've got rod 1 and rod 2 up there, made of different materials. Okay, they are connected by two different regions. So you got the two different orientations. You got 1, they're connected next to each other, and 2, they're connected kind of both to the same heat source. Okay? They can connect either way. In which case should the rate of energy transfer by the heat be larger? The answer is B, so I'm going to ask a more difficult question now to see if you can't figure this out. By what factor should it be bigger, all other things being the same? Change in temperature being the same, as well as area being, sorry, not area, material staying the same. By what factor 4 times is correct? For those of you who didn't get 4 times, see if you can't figure out why real quick. I'll give you 30 seconds, and I'll finish this conversation off. Why is it 4 times better? I will give you a hint. You should be thinking about this equation right here. There it is. Well, you said it backwards, but why should this one be 4 times as much power as the top one? Its area has doubled.
How did the area double?
Area is how much surface. Come on, come back.
Oh, I get it.
Area is how much surface is here. So now that there's 2 rods, right, that would double the amount of area, but the length is cut in half, and thus it should increase by a factor of 4. All other things being the same. Come on. All right. Now, you are definitely going to have to do this on the homework, so let's talk about this equation and why it's technically not different in the slightest. Okay, this is the exact same equation as before. I feel like the notes heard your comment about sigma and said, oh, like, we're going to hit him hard this chapter then. We're going to make sure we're getting sigma in there. Also, this is the first year I said the word sigma at all in class in AP1, and they started giggling. And it makes me worry how close Skivity is to me now. Don't like it. Don't like it. I don't. I know it's coming. I know it's coming. Okay? I offer you, by the way, a resource as a nerdy white man, and that is if you don't like a word or a phrase and you think it's dumb, I will start saying it a lot, and I think that I will get it quickest out of the popular lexicon faster than absolutely anything whatsoever. I'm just going to go around and say, that's Skivity. Skivity, Skivity, Skivity. And I'll do it all the time. I don't know if you remember the phrase, I'm going ham. I got rid of that. I did. I said, I'm going ham on everything, and now it's not a thing anymore. All right, moving on. So this equation is a new equation, and also, no, it isn't, because what this says is, what if you have multiple different types of insulation stacked on top of each other, okay? And then you'd actually have this like kind of like weird combination of like final and initial, and I can do all the math for you, but essentially, let's say I had these kind of like weird set of materials that, here we go, I've got material 1 and material 2 and material 3. Well, technically speaking, power in 1 should equal K times the area times, this would be, let's call this temperature hot, and over here is temperature cold. That would actually be, but this guy would be an intermediate step, right? That temperature is not temperature cold yet. It would be something like, let's call it TA and TB, somewhere between 100 and 0. Now, can I just say that it's 33? No, because each one of these is a different amount of insulation, and so is going to do a better job or worse job at pulling that. So this power of 1 would technically be TH minus TA all over the length. And here's the thing you should know, though, and this should make sense. Why should this make sense? That says that the amount of energy transferring through 1 is equal to the amount of energy transferring through 2 is equal to the amount of energy transferring through 3, and that should make sense, yes, because of conservation of energy. Those collisions are going to happen across, blah, blah, blah. Now, if you work all of this out, you can do this. Okay, actually, let's just do it with 2 substances so that I'm not so I'm not making this more complicated than I need to be right now. So we'll just call this is over here. This is TC, and you can do this math yourself. I'm not going to force this on you, but this would be the K of 1, K of 2, area 2 over this would be TA minus TC over length 1 and length 2. Okay, now, ultimately, do the math if you want. TA actually entirely eventually cancels out. And because it cancels out, you get to that final equation that they said a second ago, where the power, or Q over delta T, is equal to area, sure, but what are they assuming about area of all of these materials? Yeah, so in other words, when you go to calculate like your heat in your house, you don't want a large power in your house, right? You want your house to be insulated. If you want to make your house, 70 degrees, ideally, if you put it at 70 degrees and the outside is 0 degrees, what's naturally going to happen to the energy in your house? It's going to naturally filter out, right? Now, obviously, you don't want that to happen because keeping it 70 degrees costs money. So what do you do then to your house to kind of prevent that? You put in insulation. Insulation gives you these materials with low thermal conductivities so that power gets lower and lower and lower. Thus, see the picture of the guy installing insulation in this particular case. Well, what is sum of R? In all actuality, take the previous equation. Power is equal to K times area times delta T over L, and think about what variables would change in this case, and it would be these. So I can rewrite this equation, meaning I can have a larger length or a larger thickness of insulation, or I could change the type of insulation, but I'm probably not going to be able to change the area of my house in that moment. And I'm sadly not going to be able to change how much delta T there is. If I have a particular temperature I like inside, I'm not going to be able to control outsides. This, by the way, is why it's way more expensive to keep your house at a larger differential from the outside. Like if it's 100 degrees outside and you put your house at 77, you're going to use way less energy than if you try to keep your house at 70, because the difference is of course smaller, and therefore there will be less power in between the two. Versus in the winter, if you keep your house at 60 versus 0, and 70 versus 0, obviously the hotter temperature is going to be more expensive to do. But rearrange this equation and here's what you get. I'm going to do the opposite of a complex fraction thing and accidentally purposely make a complex fraction by simply, whoop, this is L over K. So the R constant is literally L over K. Why do they do that? Well, the people that make the insulation, do they get to decide how thick it is?
Yeah.
They do. They do. Do they get to decide what it's made out of?
Yes.
Yes. So turning this into a constant right here means they can tell you what that R value is ahead of time. And they don't get to control the outside and the internal temperature of your house. They also don't get to control what the area is of your house. This equation, by the way, is used by a ton of HVAC people, usually with a computer program, but essentially they use this all the time. So what does that equation say? That equation says basically if I had different materials, it would end up like this, aka it would end up as area times delta T over R1 plus R2 plus R3, aka power is equal to area times change in temperature times the sum of all of those R values. So what that means about the R value is I just showed you how you can actually calculate the R value if you know L and you know K, just using the constant from the previous page. But if it actually, so you can use this K, knowing what L is, you can get R, or here's a bunch of R values of common materials that are used. I don't know if you have any problems like this, but you've seen a lot of this stuff. Brick has a different R value than hardwood siding, has a different R value than styrofoam, has a different value of your best, where is your best guy right here? Your best guy is this right here, which you'll notice, by the way, is a stagnant layer of air, which is why the best insulation is that foam stuff, because really it's not the foam itself, but what's inside of it is just air that's not moving. That's your best insulation. And so why is air a great insulator? It's hard to make contact with air because there's not much of it. So it's really hard to hit a thing to give it speed if that's the case. That is the end of these notes. We have a lab tomorrow. Please look at the lab.